All right, Krakatoa. So what happened at Krakatoa? This first image we're looking at here, this is before the eruption. The area contained 3 volcanic islands, the largest one being Krakatoa. It was densely populated, with most of the population living along the coast, which is pretty common. But in 1883, tephra erupted, forming an eruption column and pyroclastic flow. So bad news for everybody there. Eruption was accompanied by explosions, landslides, caldera collapse, and destruction of the 2 nearby volcanoes. This produced huge waves, and after the eruption, only Krakatoa remained. So that now, if you look at the bottom image, the Anak Krakatoa, there's a small volcano that's growing within the caldera, and that the name of it means child of Krakow. And so the volcanic activity continues. We're building a new volcano where those other islands were, and eventually it will reach the size that the others were with time. So what happened there, basically the entire island exploded, created a huge tsunami, and now the island is regenerating through further volcanic activity. Okay, so there's another aerial view of the new resurgent volcano. Pretty cool. Okay, closer to home, Yellowstone. The red line in this image shows the area of the Yellowstone caldera. It formed 640,000 years ago, which geologically is pretty darn young. This cross-section through Yellowstone shows faults, earthquakes, and the position of the magma beneath Yellowstone. The extent of the ash from the 3 prior eruptions is represented on this map. One extends from northern Mexico to southern Canada to Mississippi. So this is just an enormous impact, especially if you look at Mount St. Helens from the 1980 eruption. We thought that was a big deal, and it covered this tiny area. When Yellowstone erupted on this ash bed number 3, it covered most of the continent. It's just amazing. The average time between these eruptions is about 700,000 years, and it's been 640,000 years since the last eruption. So we are due for it to erupt again because it's still over this hotspot. And we know that it's active because if you think about Yellowstone, people go there not just for its beautiful wildlife, but because they have Old Faithful, this geyser that continuously releases gas and shoots water up in the air, and so it's this main attraction. But the reason it's doing that is because this big felsic magma chamber below the surface is releasing gas, and that's what's fueling these geysers. It's pretty amazing. If you're interested in more information on this, I mentioned it earlier when I was talking about calderas, but there's a great sort of docudrama movie out there called Super Volcano, and I believe it's on YouTube in a bunch of different segments if you want to check it out. It's really good. All right. So, movement of the Yellowstone hotspot. Well, we know after talking about hotspots and plate movement last week that the hotspot itself is not moving anywhere, right? The hotspot is stationary. It's just a hot area in the mantle that extends up to the surface, and the plate above moves over that hotspot. So we can track the movement of the plate over the hotspot by looking at previous eruptions. So looking at this one, the map shows the age of the eruptions along the Snake River Plain. Magma is interpreted to be from a hotspot, and North America has moved southward over the hotspot, leaving a path across southern Idaho. The volcanic rocks are youngest near Yellowstone and become older to the southwest. And, recalling what we said about Hawaii last week and its movement over its hotspot in the Pacific, that makes sense. The further you get away from the hotspot, the older the rocks are, because it's only over the hotspot that you're generating that volcanic activity. So what does this tell us about hotspots and plate motion? The plate is moving over the hotspot. The hotspot is stationary. The plate is moving over the hotspot. The hotspot itself is stationary. How could we assess the danger posed by this volcano? So we've just looked at all the different types of volcanoes. How can we identify them based on shape and color and behavior? Now let's put it all together. What are we looking for here to assess the danger posed by this volcano? What sort of things would we be looking for? Okay, the very first thing that I want to look at is shape. Steep slopes are more dangerous. So if you see steep slopes, we may be dealing with a composite volcano, which is much more explosive, or even if it's just a smaller scale cinder cone, those steep slopes give way, right? You can have landslides when you have a steep slope. If you have a more gentle slope over a large area, maybe it's a shield volcano, maybe the eruptions are not as explosive. So shape tells you everything about a volcano. The next is rock types. So the presence of welded tuffs, pyroclastic flows, rhyolite or andesite suggest a volcano is dangerous because it's telling you this is made of felsic or intermediate composition. So what that means is when this erupts, it's going to be much more explosive because these rocks are more strongly bonded together. It's very difficult for them to release any gases, so they tend to explode. Also, if you have pyroclastic flows in the past, you know that that's the habit for that volcano. It will happen in the future. Age. The amount of erosion or actual dating of the rocks can indicate the age of the last eruption, and you can figure out perhaps how frequently it erupts. History. We can reconstruct the history from historical records and geologic studies, so that's very important. And other data, so this includes chemical compositions and gas emissions. Okay, so these are all ways that we would assess the danger posed by a volcano. I want to figure out what areas have the highest risk. Okay, so we've got Village 1 up in the upper left, Village 2 sort of central left, and Village 3 just above central on the right. So what areas would have the highest risk here? What do we want to look for? Okay, the first thing you care about is proximity. Proximity is the biggest factor in determining potential hazard. So the nearer you are to the volcano, the more dangerous the situation, the greater the hazard. So proximity is important. Next is valleys. Lava flows, pyroclastic flows, mud flows, they can all be channeled within valleys. So just like water would want to flow down the valley, lava, pyroclastic flows, or mud flows want to do the same thing. And when that happens, it gets concentrated and becomes much more dangerous. So you don't want to be in the valley when that happens. Next is wind direction. Ash and pumice are carried by the wind, and so the wind direction is very important. Most regions have a prevailing wind direction. So generally you can tell which way the wind blows most of the time and get out of the way. History. So volcanoes have peculiarities that may indicate which part of a volcano is most dangerous. So if you think about Mount St. Helens and that bulge that it had that collapsed, you might want to avoid the right side of Mount St. Helens. Other things would include mapping the actual deposits, so having a geologist go in there and draw out where the different eruptions have occurred. Seismometers to image where the magma is, so measuring the vibrations on the ground, and measuring the tilt. So keeping an eye on it and seeing are any areas bulging out or any areas collapsing. That kind of thing is going to really let you know if the volcano is active and which areas to look out for. What regions have a high risk for volcanic activity? Well, this is a pretty familiar map. We've looked at it almost every lecture so far. So again, these little orange triangles are volcanoes, and we're trying to find the areas that have the highest risk for volcanic activities. Where we find composite volcanoes, we are at great risk. So highest concentration is along the Pacific Ring of Fire, forming continental arcs and island arcs. The highest concentration is along the Pacific Ring of Fire, and it's forming volcanic island arcs and volcanic mountain chains. Okay, so for example, where we have the oceanic plate subducting below the western coast of South America, we're going to find composite volcanoes there. Opposite, where we find the oceanic plate subducting below another oceanic plate in Japan, we're going to find composite volcanoes there. Calderas. Calderas are mostly subduction related or occur in the middle of continents over hot spots or rifts, such as the East African Rift. Again, calderas are mostly subduction related or occur in the middle of continents over hot spots or rifts, such as the East African Rift. So you want to look out for those. And the last one is shield volcanoes. They occur in lines or clumps of islands and submarine mountains, such as Hawaii and the Galapagos. Shield volcanoes occur along lines or clumps of islands and submarine mountains, such as Hawaii and the Galapagos. Okay, so overall, what regions have the highest risk for volcanic eruption? We've got the Pacific Ring of Fire, at composite volcanoes, at calderas, and shield volcanoes. How do we monitor volcanoes? There's several ways that we monitor volcanoes. The first thing we look for is increased seismic activity. So we're measuring the ground shaking with seismometers. That's what we're looking at here, is a reading of seismic activity of the eruption of Mount Pinatubo in the Philippines. So that big spike is the most interesting part, right? We want to see where is the most movement occurring. In the areas where the ground is shaking a lot, where you're near volcanoes, you know that things are getting more active, things are moving. The next thing we want to monitor is increased gas activity. So instruments on the ground or in airplanes measure the amount of sulfur dioxide generated by a volcano. As the amount increases before an eruption, that may indicate the sealing of a conduit. Okay, basically, if the volcano is giving off more sulfur dioxide, they know that eruption is nearing. Changes in topography. Surveying equipment measures distance between instrument and a distant target. So that's what this image is showing us, these guys with the survey instruments. They're looking at the side of a mountain and trying to measure, is it expanding, is it collapsing, and that can tell you, is there magma directly under the surface or working its way closer to the surface, pushing things out of the way. Has magma been released already and it's collapsed? That sort of thing. So changes in topography, and then changes in temperature. So this satellite image is showing hot areas in red and yellow and cooler blue areas. So we can see the hot areas are right around the vent, and this way we can use satellite imaging to safely tell if there's volcanic activity going on, and we don't have to be anywhere near there.